In section 4.4, we're going to begin looking at real-life forces all around us and be able to take a look at some applications and some problems that are involved here. This is the section that I mentioned to you that's going to be a long section, simply because there are many types of forces and there are going to be many types of scenarios. Look how many slides are in this section, okay? So we're going to be on this for quiet. We're going to be on this for at least until the middle of next week. All right, at least, probably till the end of next week. We're going to also do 2 labs in this chapter. Okay, we're going to do 1 lab where you're going to work individually, and 1 lab I'm going to kind of do as a demo, but we're going to go through it together. I'm going to be using the front of the classroom to demonstrate it. Let me think for a sec. All right, any questions so far? I saw a hand pop up. So we're going to have 4 objectives. First, to understand the difference between weight and mass, to discuss what's called normal force, to outline different types of friction, and then to discuss and understand the meaning of the coefficient of friction. Look at the weight of an object. Now, we've referenced the word weight before. We've talked about how weight and mass are really different entities. I've mentioned that to you. But let's really go into a lot more detail now. So the weight of an object, given by F sub g, the sub is a subscript, okay? F subscript g is given as the mass times the gravitational constant, which is 9.81. Now, when it comes to forces, our free body diagram indicates whether a force is negative or positive. So here, we're actually going to use positive 9.81 for G, but then when we draw it on the free body diagram, we're going to end up drawing weight down anyway. Okay, so just trust me on this one for now. So write a little note on the side. When looking into forces, use G equals 9.81. Use G equals 9.81, not negative 9.81 here. When we're working with forces, use G equals 9.81. Again, the negative part that's kind of missing is going to come into account when we look at our free body diagram. The free body diagram is going to allow us to then solve for, say, the motion of an object or the net force on an object, but we need to be able to write draw a free body diagram to do that. So, as I mentioned in the previous class, when we draw the weight of an object, we draw it from the center acting down. Okay, that's what the weight of this object would look like. If I was just considering the weight of it on Earth or on the moon or on some planet. Okay, obviously there will be other forces acting on it. We're going to go into normal force in a minute, but you can, for now, if you want to draw the reaction force from the table at a 90-degree angle. Again, assuming this is at rest on a surface, the surface has to push back up. We'll discuss how that works and what it means in a minute. Okay, but what we're focusing on now is Fg, the force due to gravity, also known as the weight of an object.
Is it going to be kilograms or
what are forces always measured in? Newtons. Okay? So the units of mass are kilograms. The units of acceleration are meters per second squared. This is just like F equals ma. But instead of A, you have G. Okay, the units look like that. It's a kilogram times a meter per second squared, which is really a Newton. So the forces measured here are in Newtons. This is very important that you understand it's a function of the planet and the height. The number G, 9.81, is a gravitational constant on Earth. On Mars, and you did this, or on the moon rather, and you did this on your first test, there was a problem about this. It turns out that G on the moon is 1.6, not 9.81. So just look at this problem. If I want to know how much I weigh, I take my mass. Let's say I weigh 50, or my mass is 50 kilograms, times the gravitational constant on Earth, right? That gives me my weight. But if suddenly, instead of using 9.81, if I'm looking at the moon, this problem looks the same, except this is now 1.6. So this explains why in those videos you see the astronauts kind of moving much easier, the way they're walking. Gravity is not affecting them as much, so you can jump much higher on the moon. Gravity is physically pulling you down with less force. You can see it in red right here. Kim? Yeah, so the problem, if not given any information, you assume is the Earth. If you need some other piece of information, you'll be given that information. Okay, and we'll see that in the first example. So we get the idea that mass is constant, weight is not. Weight changes depending on the planet. When we look at force of gravity, when we look at the force of gravity between two particles at a certain distance later in the year, we'll see that it also changes as you change altitude. So if I'm here, and I alluded to this with the Denver's Mile High Stadium, okay? So if you are at a higher elevation, you actually weigh less. The force of gravity is less on you. That's why you see a lot of home runs and long field goals in football when you're playing in Denver. You're playing either in the Colorado Rockies Stadium or the Denver Broncos Stadium. Okay, because of that elevation. That's really the reason. So force is a function of planet and elevation. Okay, planet and elevation.
1.6 is gravity.
This is the moon here I was giving you a little tidbit about. Yep. All right. If an object's mass is 25 kilograms, what is the magnitude of its weight on Earth? What does the word magnitude mean? We've used it maybe once or twice all year. It was real quick. We used it when we made when we differentiated between velocity and speed. For example, ready? I'm walking this way. My velocity might be negative 2 meters per second. What's my speed?
2 meters per second.
Just 2 meters per second. Thank you. So what did you do, Johnny? Yeah, you ignored the negative. Same thing here. So when a problem says, what is the magnitude of the force? I'm not asking about the direction. It just says magnitude. So your answer is just in newtons. Doesn't matter if the force is up, down, left, right. Makes no difference here. Okay? So again, although the force acts down from gravity, we're just giving a numerical answer here, not the negative or positive sign to indicate up or down. So what is the magnitude of the weight of this object on Earth? And then what is the, what about on Jupiter, where the acceleration due to gravity is 2.64 times that of Earth? Okay, so it's 2.6 times more, or a factor of 2.64 increased by that 9.81. So a factor. So let's do the first part, which is easy, then the second part, which is not so hard either. So my formula from the last slide is just an ice maker. My formula from the last slide is?
F equals mg.
Yeah, Fg equals mg. It's on your formula sheet. It's on your formula sheet. But by the end of this section, this should be memorized. Fg equals mg. It's just like F equals ma. But a is just gravity now. It's the acceleration on Earth. So we take 25 kilograms.
245.25.
245.25.
Is it still N? Yeah.
Yep, newtons. Still have newtons. Again, kilogram times meters per second squared. That's the easy part, obviously. Let's take a look at the next part. It says, what about on Jupiter, where the force of gravity is 2.64 times that of Earth? What am I simply going to do to make this easy on myself? There's an easy way to do this problem. What would the easy way to do it, Jess?
Just times 9.81 times 2.64.
Yeah, so on Jupiter, it's still 25 here, but it's now 9.81 times 2.64. Because it's 2.64 times that of Earth. I could also have just taken my answer from the last part and multiplied by 2.64. All right?
647.46.
What do you got?
647.46.
All right, so again, if you had taken the answer here and multiplied by 2.64, you get the same answer at the end. Okay? And that's what Jess was saying by multiplying by 2.64 here. Okay, because it's larger gravitational pull. Jupiter is much more massive than the Earth, believe it or not. Although it's made of mainly gases, it's actually more massive than the Earth is, so it has a higher gravitational pull.
I heard that.
Any questions on this? Pretty simple so far? We need to learn about the basic fundamental forces so that we can then analyze a problem where there are several forces acting at once. So we're going to look in a moment at problems where there's a force of tension pulling on it, there might be a pulley somewhere, there's gravity pulling down, there's friction on the floor, there's the normal force pushing up, all at the same time. So what we're doing is we're starting section 4.4 by analyzing each individual force first. So it will help us understand the smaller components, and then we can build up to that larger concept. Okay? Normal force. Okay, at normal force. So can I get someone just to read nice and simply for us, nice and loud, Cooper?
Normal force, the reactive force that acts on an object in a direction perpendicular to the surface Fn.
So we know that we've talked about this reaction when you put something down. So you put it down, the table pushes back up. That's called a normal force. Now, it's not normal for any other reason besides a mathematical term. And let me explain what normal means. So draw yourself a table surface. Okay, put some legs in the table maybe. Then put an object on that table. Now, the way it works is as follows. The table pushes straight back up, perpendicular to the surface. But it's perpendicular to the surface in two directions. It's perpendicular like this, and it's also perpendicular in this direction. You see the two perpendicular angles I'm drawing in? So it's perpendicular to the surface in all directions. That word in mathematics is called normal to a surface. So here, take a look at my stylus. And here's my iPad. This would be normal to the surface. It comes straight up out of it. It's perpendicular in all directions. If I tilt it at any angle whatsoever, it's no longer normal to the surface. Normal to the surface literally means like the way a tree comes out of the ground or the way a building is built on a surface. It's all right angles along the side of the building. That's normal to a surface. So normal force is defined as the force acting normal or perpendicular to the surface. It pushes back up. Now, there's a common misconception. Right now, if I put this iPad down, the normal force is equal to the weight pushing down because it's at equilibrium. It's sitting still. Weight is pulling down with maybe like 2 newtons. Normal force pushes back up with 2 newtons. So there's a common misconception that the normal force is always equal and opposite gravity or gravitational force. That is not true. Let me give you a quick, simple example of why. An easy way to see this. Draw yourself an inclined plane and then draw an object on the inclined plane. Gravity pulls straight down, but the normal force always acts perpendicular to the surface. Since the surface is inclined, the normal force acts at an angle in this diagram. So we're going to see inclined planes a lot in this section. Inclined planes are very useful. So many things are modeled after inclined planes. You want to do anything with construction. A screw is an inclined plane wrapped around a cylinder. That's all it is. That's physically what it is. You want to move things. You want to build things. You always have inclined planes. Beams, trusses that go across something are like inclined planes. So we're going to really study them, but this is an easy example to see that normal force is not equal and opposite of gravity always. Okay? It's not always going to be equal and opposite. Another way you can see that is as follows. I'll give you a simple example that's a little more obvious to see. Here's my water bottle. Okay? Put the water bottle down on the surface. Let's say it weighs a newton. So the surface pushes back up with a newton, right? Easy enough? Now, watch what happens. I hook my finger under here and I start lifting up. But I'm only pulling up a little bit. What's physically happening? It's starting to tilt. I'm starting to pull it up, but I'm not pulling it up off the surface yet. So although I may be applying like a half a newton up, gravity weighs a full newton down. So what I'm doing is I'm helping out the normal force until I pull up enough that what happens? And now what's the normal force? Yeah, there's no normal force because it's not in contact with the surface. So literally this is what's happening, and we can demonstrate. I'll show you with, we can see it with a force scale, and we'll show it on the computer maybe next week in the beginning. As I lift, the normal force decreases and decreases and decreases until I lift enough that it becomes 0 and it lifts off the table. So when you pull up on something, you're helping out the normal force. You're making the table do less work. And you can see that if you look at somebody who lifts weights, a bench presser, lays down and they start bench pressing. What if somebody can't lift the weight off their shoulder? What does the spotter do? The spotter comes in and helps lift the bar and put it on the rack. Well, the person that's pushing up is like the normal force pushing up. If there's no normal force, that bar would fall back onto their chest. So they're like the normal force. But if the normal force isn't really enough, or if they're pushing up and somebody comes over and just starts helping you, isn't it a lot less for you to push up on suddenly? It's analogous to a normal force. So the table's pushing up, but if I start pulling up on the bottle, I'm helping lift some of the weight. So the normal force, instead of responding with 1 newton, because say the water bottle was 1 newton down, the normal force is no longer 1 newton up. Maybe it's only like 0.7 newtons, because I help it out with a 0.3 newton pull. Until I pull up enough with 1 newton, I lift it off the table. So the normal force can vary. It is not always equal and opposite the weight of the object. All right? Let's look at an example of this where we have 2 stacked. Oh, wait. I jumped ahead. The next one's 2 stacked. Let's look at this one first, where we have an object being pulled on. So an object is at rest on a table with a mass of 10 kilograms, and you're trying to lift it up with an upward force of 35 newtons. Will it lift off the table? If not, what is the normal force that's exerted by the table? So we've got givens. List the givens. What do you got?
Your M is 10 kilograms.
Good. Next. Keep going.
Then is 35.
F what? Read what it says. You are trying to lift it up, right? That's a pull, isn't it? FP.
Yeah.
Okay, so you're trying to lift it up with 35 newtons. That's FP at the top of the diagram. I gave you a free body diagram in this example just to simplify it. The next one we'll make our own. Weight is pulling down. That's FG. If I want to figure out what FG is, I know that FG is equal to mg. I remember that. I can leave the variables for now because I know what mass is, so leave it in variables. And then the question mark is, what is Fn really? All right? So if I look at this problem, when will the object lift off the table physically? If I start to pull up on your calculator and it's not lifting, I can't lift it, it's too heavy. When would it lift off the table? When what? When I give it enough force. So if Fp is bigger than Fg, then it lifts off the table. Does that make sense? If I pull up with more weight than it is, it lifts up. But if I only pull up with a half a newton of force and this weighs a full newton, it's not going anywhere. So let's determine what Fg is. Let's see what the number is for Fg. So it's 9.81 times the mass, which is 10 kilograms. I should probably write that as 10 then times 9.81. Okay, giving me a force of 98.1 newtons. Focus, Andrew, focus. So, I can look at this problem and I can say, the force I'm pulling up with is clearly less than the weight of the object. So am I going to be able to lift this off the table? No, I'm not. But I'm helping out the table. I'm helping it by pulling up with 35 newtons. So the normal force doesn't have to do as much. But again, this object isn't moving. So what we do is the following. For this next part, to find out the normal force, we look at our free body diagram and we say the sum of the forces in the y direction equals ma. Again, Newton's law, sum of the forces equals ma. I'm specifically looking in the y direction. Okay, I'm specifically looking in the y direction. I pull on this object and I pull and I pull and it doesn't move. It still doesn't move. So what's the acceleration? It doesn't move. Zero. Again, an object moving free in space, what we studied last chapter, it was moving through the air. That's why acceleration was negative 9.81. It was pulling it down. It was moving physically. This is not moving. So the acceleration is zero. So the sum of the forces in the y direction is equal to zero. Well, what are the forces in the y direction? What's acting up?
35.
Give me the labels. Acting up. Labels, units, variables.
FP.
Good, FP's up. What else is up?
FN.
And down?
FG.
So I've got Fn is up, Fp is up, Fg is down, and that equals 0. Okay, again, Fn is up, so I leave that as positive. Fp is up, I leave it as positive. Look at Fg, it's got the negative sign. That's why you don't need the negative for the 9.81 when you're doing these problems. Because the negative sign comes from the free body diagram, which indicates that weight is pulling down. Next, all I need to do is plug in my numbers. Fn is what I'm looking for. Fp is 35 newtons. Fg is 98.1 newtons. And I can solve for Fn. Okay, add 98.1, subtract 35. I get
63.1.
Thank you. Somebody verify, obviously, but it sounds good to me. Okay, now, why is the normal force less than weight? Because you're helping on the object a little bit. You're giving it 35 newtons. The normal force is giving it 63.1 newtons, and as a result, that's equal to the weight of the object. So, here's a multiple choice question. Ready? guaranteed kind of multiple choice on your test. This theory, the way I'm saying it. Ready?
Hold on.
If you increase your pull on an object and it still doesn't lift off the table, if you increase your pull but it still doesn't lift off, what happens to the normal force? It what?
It goes down. It goes down.
Why does it go down?
Because even though you're not lifting it off the table, you're lessening the help force.
You're helping, you're lessening what's left over. So if this wasn't 35, if this was like 60 newtons, I doubled my force, 70, I doubled my force, it still wouldn't overcome the weight, right? But if this were 70, now this would be 28.1, bless you. This would be 28.1 right here. So the more you, God bless you, the more you pull up on an object, even if it doesn't move, what you're doing is you're lowering the normal force that the table has to push back with. Okay, you're lessening or decreasing the normal force. Okay, this is the kind of question that you could expect for a multiple choice, where the answer choices are remains the same, increases, decreases, or I don't know, maybe like doubles or something that's completely wrong. All right? That's the kind of thing you would see.
It lessens the normal force. The normal force lessens.
If the FP goes up, FN would go down in this problem. Again, this is specific to this example. As FP increases here, FN goes down. Once FP becomes as much as FG, then there's no normal force anymore. It just lifts off the table. Okay, again, once FP overcomes FG, once the pull overcomes the weight, it just lifts off the table and there would be no normal force left. Normal force cannot be negative. So once you lift off the table, it's just not there anymore. You can never have a negative normal force, okay? It's a reactive force. It's always pushing back up against gravity. Peter.
How does the normal force change?
How does it change?
How does the table have the ability to have different normal forces?
Because as I lift up, I'm lessening the weight of the object. So the table doesn't have to provide as much resistance. It doesn't know it's doing it, it just reacts that way. It's a natural reaction in the world. When I'm walking on the ground, watch. The ground is a normal force pushing me back up. But if suddenly I grabbed onto like a cord and that cord started pulling up on me, but it didn't lift me off the ground, I would be kind of like almost suspended, but the ground would still be pushing up, but with not enough force, or not as much force. So the normal force varies on its own. You don't do anything. It's a reactive force by nature. So we got 10 minutes.
We have 9 minutes.
Let's take a look at this example now. So, a small object is stacked on top of a larger object, and they're both on a table. Draw it right away. Draw it, please. Small object on top of a large object on top of a table. My art skills are fabulous. So, tables or walls are just dashed lines. Okay, it just means a surface.
All the girls found that really funny.
Those are not, who would have thought? Those are not legs right here, each of these. It just means a surface. Okay, it just means a surface. The small object, guys, focus back there. The small object is 5 kilograms in mass. The large object is 15 kilograms in mass. What is the normal force acting on each object, on each individual object? Okay? It's a great question.
I think so, yeah.
Let's isolate these objects. Let's draw the small object here, and let's draw the large object here. We'll draw some free body diagrams to help us. What is pulling down on the small object? What force?
G.
Yeah, Fg, or force of gravity. What's pushing back up on the small object?
FN.
We'll say Fn1. You could say P, it's not a push, it's a normal force really. Fn1. Okay, that's the small object. That's literally all that's happening.
What is the box in the middle? That's the large one.
The large object. Yep.
FN stands for?
Normal force.
So that'd be 5. No.
No. That's a mass, right? The big object. The big object. What is pulling down on it? Pulling down on it.
The force of the small box and gravity.
Yeah, both the force of the small box and gravity. So here is the weight of the first object acting on it. And here is its own weight. And then reacting back up is Fn2. That's an ugly 2. No. Trying to overwrite that 2 and it's not working with me. It's a different app. Once you're outside of the object, it doesn't allow you to erase it, unfortunately. It's a presentation app. Everything about it is awesome except that one feature.
So are you going to write them a letter?
I've already.
No, you haven't.
I have. I emailed them. It's like a help thing you can email. They gave a reason which I understood, but
What was the reason?
it's because you're able to select multiple things at once now. Like if I hit the X now, I can select this entire thing and delete it all at once. And they think that that's more useful than individually erasing spots. I think that this should just be an X feature and then an eraser feature separate. But the eraser turns into an X once you're off the
So
feature.
what's unique, the eraser or the pen?
Watch, right now if I hit eraser, I can't erase anything. I'm not, because right now I've exited those features. But if I have a line here and I don't exit it, I can erase it. Whatever, it doesn't matter right now. Anyhow, so this is the problem. We've got what's going on here. So let's take a look. Neither of these objects are moving. So the sum of the forces that equals MA in both cases is going to end up being 0 for both. Okay, so I can make this a little bit simpler here. For object number 1, for mass 1, I say that the sum of the forces equals MA. What's acting up for object 1? Just look at the free body diagram. You're literally, this is the thing last year that I noticed students had trouble with. If you don't make a free body diagram properly, you're not going to end up getting the right answer. So if you don't make this part right, this next part is going to make sense. Okay, so literally look at your free body diagram. Fn1 is acting upward. And Fg1 is acting downward. And it's not moving. It's not moving up or down. There's no acceleration. So this just becomes 0 here. So that's the equation of forces for the first object. Try and write the second object on your own.
If that's a Y next to the F, is that Fy or G?
Fg.
Oh,
Fg. Write the equation for the second mass, please.
for the second box?
Yes.
Did you say FX or?
It's still vertical, so it's still Y. So right now we've only looked at vertical forces, so everything's in the Y direction. We'll look at forces at angles, which are both, like we did with velocity, the same thing.
Isn't it the same?
This is not the same, this answer here.
It's not?
We've got Fn2 acting up.
Yeah.
That's kind of the same. But acting down, we've got the sum of Fg1 and Fg2.
Okay. So it's minus Fg1 plus Fg2?
If you put them in parentheses, you can put it like that. That's fine.
If I put this
Yep, put the sum of them in parentheses. I'm just writing them out separately. Literally, guys, all I do is when I see an arrow down, I put a negative in front of it. So Fg1 and Fg2 had arrows down, so I put negatives right here. And then Fn2 was positive because it acted up. So those are the equations for this. And if I'm trying to find the normal force for each, solve this for Fn1. I just add Fg over. So Fn1 is just really the weight of that upper object. So Jack, it wasn't 5, because 5 is the mass, right? But you had the right idea. Okay, so Fn for the first object is really just opposite of its weight. The weight of the first object is the mass of the first object times gravity, or 5 times 9.81. So we have 49.05 newtons. Okay, that's the first mass only we solved. So we looked at the first mass equation. We're looking for the normal force, so we add Fg1. We take this Fg1, add it over, giving us this. The force of gravity, or the weight, right? The weight of the first object is mass times gravity. So you take the mass of the first object times gravity, 5 times 9.81. This gives you the force acting up on the small box.
Is that formula always going to be, like that formula's never changing?
Everything changes with every single problem. You're never going to have the same answers over and over. That's the thing about forces. You know what formula doesn't change? F equals ma. That's why that formula is so important. F equals ma never changes, but depending on the scenario, the equation of forces that you're seeing right here, this equation can vary, like it did right here. See how it varied? In this one, it's a little bit different. It's similar, but we have the FG2 acting also.
I just don't understand how if it's Fn1 is equal to Fg1, why are we multiplying?
But what's FG1? It's the weight of the first object, right? Isn't FG1 the weight? And isn't weight equal to mass times gravity?
Okay.
That's what I'm doing. I'm replacing or substituting the formula for Fg with m1 times g.
Okay.
You can figure out what Fg is in the beginning of the problem and just plug it in. That's fine. But I'm just using the
I
formula.
just wasn't really sure what
Please
that
multiply
meant.
your final answer by 3 for the top one. It's 15.
It will be 4 times this actually, because 1 plus the 3 is 4.
But that.
Sure. Yeah. If you see that, that's fine, Jack. But you have to make a statement at least. So if I solve, take a look. I'm going to solve this equation right here for Fn2. You really need to look up, guys. You need to all be looking up because you're going to make these mistakes. These are negative. So I move them over here by making them positive. Okay, so Fn2 equals the sum of these. So 49.05 was this one. This is going to be 147.15. We're going to add those two numbers together. Where am I getting the 147.15? Mass times gravity. Mass times gravity. Okay, that's where I'm getting this right here. Okay, if you felt like you were a little confused, you might want to just rewatch my video that I've recorded for this section already. Just watch the first 2 examples that we've done, that's all. Okay, look at it again and slow it down for yourself.